Good day everyone. Today I will be answering questions 7 and 8 and problem 18. And question 7 is, how many lines of force must be cut per second if 1 volt is to be generated in a moving conductor? And the answer is 100 million lines of force. This 100 million lines of force is equivalent to 1 Weber, and 1 Weber is equals to 1 Tesla square meter, which is also equals to 1 joule per ampere. So question number 8 is, in an actual generator, what effect has the number of parallel paths in the armature winding upon the terminal voltage? So, parallel paths determine the current and voltage rating. We can incorporate lap winding and wave winding to parallel paths. So here, for example, we have 96 conductors and 4 poles. For lap winding, the number of parallel paths is equal to the number of poles. So we have 4 as the number of parallel paths. For wave winding, when we have 4 poles, then the number of parallel paths is 2. Now, we take the numbers of conductors per path. Z over A. Our Z is 96 and our A is 4. Now, the conductors per path is 24 for the lap winding. For the wave winding, we have 96 conductors, then the number of parallel paths is 2. We have 48 conductors per path. To illustrate that, we have here the figure for lap winding. It said that in each path there are 24 conductors. So here, first conductor, second conductor, so on and so forth until we reach the 24th conductor. And for the wave winding, it said that there are 48 conductors in each path. So here, first conductor, second conductor, so on and so forth until we reach the 48th conductor. So why is that lap winding is used in high current rating and low voltage rating, while wave winding is used for low current and high voltage rating? To understand that, for example, there's 1 volt in each conductor. So in this series of 24 conductors, given that they have 1 volt, 1 volt, 1 volt each, then the total number of volts for the lap winding is 24 volts. While for the wave winding, when we have 1 volt until the 48 conductors, then we have obviously 48 volts. Now we can see that wave winding has higher voltage than the lap winding. Problem 18 is, what must be the total armature winding current in problem 17 if the torque increases to 1,200 pound-foot and the flux density decreases by 4%. So the given are, armature slots is 72, conductors per slot is 6, pole arcs covered is 70.5%, the flux density is 58,000 lines per square inch, length is 8 inches, torque is 1,050 pound-foot, armature core diameter is 21 inches, the number of armature paths in parallel is 6, and the current and force is missing. Now in question 18, flux density decreases by 4%. To get that, we multiply 58,000 by 4% and deduct it from the original value, which is 58,000. We now have the new value of flux density, which is 55,680 lines per square inch, and the torque increases from 1,050 to 1,200 pound-foot. Now, first thing we should do is we investigate the given if they have the same units. Now we can see that the torque has different unit from the other given. It's better to say that we convert torque rather than the other given, because it would take a lot of time converting other givens just for the unit of torque. Now we have I and F as missing, and we all know we can get force if torque and diameter is given, since the formula of force is T over R and R is just D over 2. Now convert the value of the torque, which is 1,200 pound-foot to pound-inch. We multiply 1,200 by 12. The new value will be 14,400 pound-inch over our radius, which is 21 over 2, That's 10.5 inches. And now we have force is equals to 1371.43 pounds. We substitute all the given from the formula. F is equals to V times I times L over 11,300,000 pounds. Since we are using pounds, we have this constant. Plug in the given to the formula. Force as 1371.43 pounds here is equals to flux density, which is 55,680 lines per square inch, times its length, which is 8 inches, times I, which is missing, and we know that we have 72 slots, and each slot has 6 conductors. So 72 times 6, and it covers 70.5% of the circumference, which is 0.705, all over the constant, which is 11,300,000. Now we have the new value of current, which is I is equals to 114.23 amperes. So that's all. Thank you for watching, and I hope my video helps you. Like, comment, share, and subscribe. Peace out.